Okay, so let us get going on ordinary least squares. In the last class, if you recall, we formulated the least squares problem, and I also talked about the projection theorem. We talked about a theoretical version of the least squares, the sample version of the least squares. It is a sample version that we are mostly interested in, because that is a problem that we will be solving and applying as well. And I said there are several ways of solving the ordinary least squares problem. One is through standard optimization techniques, other is using the sum of squares methods, and third is through the projection theorem. And in fact, I gave you a statement of the projection theorem in the last class, which this projection theorem itself stems from, you can say, vector algebra or linear algebra, so to speak. It talks about projecting a high dimensional vector onto a low dimensional space in an optimal way, and the optimality is in terms of minimizing the sum square approximation errors. So, you should get used to these terms if you plan to work in data analysis and you want to be clear about terminologies, then you should get used to terms like projections, approximations, predictions, estimation, and so on. Projection is the same as approximation, approximation is the same as prediction, and prediction you can say also is the same as filtering. So, there are all these terminologies are equivalent in some sense, and that it is just a domain and the context which will dictate what term to be used. So, we apply this projection theorem, and this projection theorem clearly says that any vector can be projected, of course, provided it lives in the Hilbert space. It can be projected onto a low dimensional space in a unique way, such that they are the sum square 2 norm, or sorry, the square 2 norm of the error is minimized, and this is achieved when the error is orthogonal to the regressors or the space spanned by the regressors. Now, qualitatively what that means is there is nothing left in the error that can be linearly explained by the regressors. Okay, that is what it means, because we are talking of orthogonality, and I have talked about this in the last lecture. There are always parallels between linear algebra or vector algebra and statistics. In statistics, we use the term uncorrelated, and the equivalent term in linear algebra is orthogonal. We know what uncorrelated means. When two variables are uncorrelated, that means one cannot be explained by a linear function of the other. Likewise, here orthogonal would mean that there is no projection or there is no shadow, you perfectly, when the regressor is perpendicular to the prediction error, like I showed you geometrically in the last class. So, that is the trademark feature of so called least squares solutions. So, how do we apply this theorem in solving the least squares problem? It is very straightforward. In the last class, we had used this notation. We said yk equals sigma. I used x. I am going to first talk about that. So, you have x transpose k theta, or you can say xik theta I. This is the approximation, but in the equations that I show you on the slide, we have a different notation for the regressors, where we replace x with this regressors here, which can be of course written in a vector form. Notice that theta we have here p parameters or p regressors. So, theta is a p by 1 vector, and so is this psi k. It is nothing but a collection of these p regressors at the kth instant. By convention, all vectors are column vectors, and therefore, we have a transpose there. And then we had also defined these matrices phi, the big phi, which is now stacked across observations. So, this small one is stacked across regressors, and the big one, now you take this vector and stack it across time. Then you get a matrix, and that matrix is phi, and it is of size n by p. Now, you may be wondering what happened to all the notation that we have been using for time series and so on. Well, when we learn estimation methods, it is best, in my opinion and in my experience, to learn the most generic formulations of these problems and then apply as needed. So, I will show you for example very shortly how do we set up the least squares problem for estimating AR models, right. There these regressors will have a meaning. Right now they are just regressors, generic regressors. Okay. Now, so the vector form of writing these equations is y equals phi theta. So, you should also get used to this notation. Now, phi is a matrix of n by p, theta is a matrix of p by 1 and y is a matrix of vector of n by 1, it is a vector of observations. In fact, strictly speaking this should be y hat. So, how do we now use the projection theorem? We want to obtain the best approximation and we want to find theta such that what is minimized, the square 2 norm of this vector is minimized. Now, we see the setting very clearly. The projection theorem says that assume now all our vectors live in a Hilbert space, and do not ask me how do you know, okay. I do not know, you do not know. So, let us assume something that for the benefit of the mankind that yes it lives in Hilbert space and proceed. Of course, you can argue, that is if you use the stationary, when you apply to time series modeling you can ask what does it assumption of Hilbert space mean there. At the moment we will not go into that. Now, the projection theorem tells me if I want to find a theta, right. So, what we are doing is we are writing y equals y hat plus some epsilon. Epsilon is also a vector, y hat we know is phi times theta. What the projection theorem says is, as long as you want to break up y into two parts such that this is minimized, then the solution is always such that the epsilons are orthogonal to the space in which the predictions lie or the projections lie. Y hat, now this equation tells me what makes up the projections. So, y hat now is in the space of regressors, right, and therefore, we require that for the solution epsilons be orthogonal to the to each of those regressors, because y hat is made up of those, is spanned by those regressors. That is it. So, you apply this relation instead of using uncorrelatedness we are using orthogonality. Here remember there is no notion of randomness, there is nothing, we let go of randomness for a while, live happily. And now we say that since epsilon is orthogonal to every regressor, the inner product, in fact strictly speaking the dot product, but we will use the dot and inner product interchangeably, the inner product is 0 for every such regressor. So, that is your equation here on the top, and that is it. So, you use a simple formula for writing the dot product. You know that the dot product between two vectors x and y is x transpose y, and that is all I have written there, there is nothing magical there, and you write this for every regressor. That means you have p such equations, right. So, look at the beauty. What has happened here is, when you look at this problem, remember you have theta which is unknown, phi is known, y is known. So, if I were to replace y hat here with phi times theta, and if you just look at this equation, we have a set of overdetermined equations, right, from a theta standpoint, but if you also include epsilon which are also unknowns, they are not overdetermined. But normally we do not count epsilon, we say that that is an approximation error, I do not want to estimate the error, I am only interested in estimating theta. From that viewpoint you can say it is overdetermined, and what we end up doing in solving the least squares problem is we take the problem from an overdetermined framework to an exactly determined framework. That is how is this true? Because you look at the equations that we have set up, we are saying psi I transpose times y minus phi theta equals 0, and this is for every regressor. So, I have p such equations and I have how many unknowns? P unknowns. So, I have p equations, p unknowns. So, look at the beauty, we have now translated the problem of an overdetermined problem into an exactly determined problem. you should as a thought process, as a reasoning process ask, why did not I do this in the raw domain? What I mean by raw domain is in the measurement domain. I will be more clear. To start with, I have p unknowns and I have n observations. What am I doing here from a curve fitting standpoint or from a functional fitting standpoint? I am trying to find the best fit, right. I am trying to find the best approximation, but I could have also solved a simpler problem. I could have said I will randomly pick p observations from n, right. I have n observations, I just need p equations for p unknowns if I want my life to be easy. I could have randomly selected p observations from n unknowns and force fit exactly my y to match with my phi theta, right. I could have done that. What could happen? Is there something wrong with that approach? Sorry? That is a bit beyond in simpler terms. So, you understand my statement? I have n observations and I have p unknowns. I just need p equations. Somewhere I have to beg, borrow or steal, I have to get p equations. No, why? I am going. So, what I am doing here is in this equation I am saying phi theta will never fit any of these observations exactly, right. Phi theta is a prediction or the approximation of y. It does not fit any of the observations exactly. It leaves an error in the prediction of every observation. On the other hand, I could have said, why should I do that? At least let me satisfy exactly p out of n observations. Am I right? I am unable to satisfy the n observations, any of the n observations exactly. That is what this equation says. On the other hand, I could have forced my theta, because theta is the decision variable. I could have solved a different problem, not a least squares problem. I could have solved a different problem and demand that my model fit p, any p out of n observations exactly. Sorry? Okay, let us say there are no outliers, clean, very clean data, clean in the sense no outliers, no data pre-processing required, Shuddha data. Sorry, what variance will?
When you are trying, when you are given an additional, once you find this, you get an additional point. If it does not come in that point, then the error will be high. You won't pick the data.
I can always, I can force fit. See, the reason I am asking this is for you to understand the basic philosophy of least squares. If you are able to answer the question that I have asked, you will appreciate the least squares a lot better. You will, I can randomly pick p observations and force fit, and I can argue that look, at least p observations have been fit exactly, n minus p have not been fit, correct. So, what do you think least squares is intuitively doing for you? In what? Prediction of what? You have to be very clear, you have to articulate clearly. No, there is no realization here, no, nothing. When I do not talk about randomness, do not invoke randomness, okay. Sorry? See, you should understand that ultimately we are solving p equations, p linear equations. With the least squares, those p linear equations happen to be the ones that I have written, that phi transpose times y minus phi theta equals 0. Those are the p equations I am solving. All I want you to answer is, what if I had set p equations in the observation domain? Straight away, I could have randomly selected p observations. If you look at these equations, the one that come out there, what you are essentially solving is phi transpose phi times theta equals phi transpose y. These are the, do you realize that phi transpose phi is p by p, correct, because phi is n by p. So, phi transpose phi is a p by p matrix, phi transpose y, what is the dimension of that? P by 1. So, I have p equations. these are also P equations, and the other one that I have asked also has P equations. What is the difference in the nature of these two solutions? This is a least square solution, it minimizes the sum square error across n observations. In the other case, yes, I can force fit the model, which is phi theta, to exactly explain P out of n observations, but what happens is when you use that model to predict the remaining n minus P, the variance of the error, that is a sum square error, let me not use the word variance, the sum square error that you incur for the remaining n minus P is going to be larger than the sum square error that you will incur with this least squares. So, now you should understand the philosophy of least squares better, right. Essentially I can fit the model, yes, it will exactly explain P, but you would have lost out on the sum square error for the remaining n minus P. If you say those are the ones that are very important to me and n minus P are not so important, it is a different problem. Then you are talking of weighted least squares problems. Now you also understand why this is called ordinary least squares. In ordinary least squares, we are giving equal importance to all observations. We believe that every observation is important, is as important as the other one. Whenever you have such a setting, we call this as an ordinary least squares. Okay. So, essentially what we have done is we have translated a bunch of overdetermined equations to an exact set of equations. When you read the literature on least squares, they will say exact set of equations in the covariance domain. Why do we call this as a covariance domain? Imagine that you are actually multiplying both sides with 1 over n, and this is useful, this interpretation. Now you can look upon 1 over n phi transpose phi as an estimate of the, if you think of size as some random variables and y also as another random variable, then 1 over n phi transpose phi is an estimate of the variance covariance matrix of the regressors. Okay. Assume that they are 0 mean. So, if you expand phi transpose phi, what do you get along the diagonals? The sum squares, right, 1 over n sigma psi I squares. That 1 over n sigma psi I square is an estimate of the variance, assuming it to be 0 mean, of the respective regressors, and off diagonals will carry the estimates of the covariances. In other words, 1 over n phi transpose phi is an estimate of the covariance of the regressor vector, and phi transpose phi is the cross covariance, is an 1 over n phi transpose phi y is an estimate of the cross covariance. So, what you are essentially doing, if you recall the theoretical least squares problem, that is what we had, right. We had the big sigma psi theta equals the big sigma psi y or x y. There also you had P equations, but again in terms of the covariances. So, why did we move to the covariance domain? In moving from the measurement domain to the covariance domain, what we have essentially done is we have taken care of these errors that we are incurring in this approximation. In fact, there is another perspective that we will learn later on, but you have to understand least squares from various angles, and for a long time the story seems never ending. You can develop so many different perspectives. All right. So, that coming now to the solution, assuming phi transpose phi is not singular, you can now write the solution as phi transpose phi inverse times phi transpose y. This phi transpose phi inverse times phi transpose is called the left pseudo inverse of phi. Remember, your phi is a rectangular matrix, it is n by p. There is no notion of inverse in a standard sense, but if you were to write, if you were to left multiply phi with phi transpose phi inverse times phi transpose, then you would get an identity, but this identity would be of what size? N cross n or p cross p? P cross p, right. So, this would be p cross p, and then likewise you have a right pseudo inverse, which we do not use, we use what is known as a left pseudo inverse. Why is it called pseudo inverse? It is as if you know, instead of solving this, suppose I am force fitting. So, I am solving y is approximately equals to phi theta, right. Imagine that there is an equality here, this is a set of over determined equations. If I had exactly p equations, then I could have written theta as phi inverse y, but I do not have exactly p equations, I have more than necessary. So, what I can think of is now, okay, let me even write this and multiply both sides with phi transpose. The same equation I am just multiplying both sides with phi transpose, right. Now, and also multiply both sides with 1 over n if required, if not it is okay, it does not matter, you do not need the 1 over n to get the interpretation. This 1 over n is needed if you are thinking of phi and y as random vectors, if they are not, then you do not need the 1 over n. So, momentarily forget the 1 over n and recognize phi transpose this epsilon to be a vector of inner products between the regressor and the error, right, because what is phi made up of? It is made up of different regressors. So, if you were to expand phi transpose epsilon, what is the size of phi transpose epsilon? It is, yeah, you should get used to these dimensions. So, it is p cross 1, p cross 1 vector of what? P cross 1 vector of covariance between the regressor and the error. And now you use the orthogonality property and say that I will choose that solution where these inner products are 0, then you get the least square solution. But in some sense this is called pseudo inverse because you are kind of force fitting and phi theta onto y, and then you say, well, can I write theta as some inverse of phi times y, okay, this is a dagger symbol here, and I want this solution to be optimal in some sense, that if you use the pseudo inverse, what is the pseudo inverse? Phi transpose, phi inverse, phi transpose. So, that is a pseudo inverse perspective, that is why it is called a pseudo inverse. Of course, this is the main reason why you call this as a pseudo inverse. It is not an inverse in the traditional standard sense. And in MATLAB, for example, you would use p in R, there is no inv command in R. You know why? So, the direct inversion, the formula that we learn in high schools is not numerically friendly. It can result in large errors, particularly when the condition number of phi is high. So, what people do is in computing the inverse of phi, look at the entire spectrum of theory that is available. There is theory, right, which is a theoretical least squares problem, then you have the sample least squares problem, and then there is a numerical implementation of it. The numerical implementation of least squares is done through either QR factorization or singular value decomposition. One of these is used in implementing the least square solution. What we mean by implementing is in calculating the pseudo inverse, this part here. I am not going to go over the details, these are standard stuff you should be able to find, it's there also in my textbook in chapter 14 at the end of the chapter, or you can find it anywhere in a good linear algebra book. In R, the solution is obtained by using the command qr.solve. So, if I want to find the inverse, pseudo inverse or inverse of any matrix, even square matrix, there exists no in command per se. So, for example, so let us generate a random matrix here, maybe a 3 by 3, and to indeed check it is 3 by 3, type out A, and then you just use qr.solve A. Okay. So, qr.solve A should give you the inverse of A. In fact, in MATLAB there is something called p-inv, pseudo inverse explicitly, which uses SVD. Okay. So, there are two different algorithms, both are numerically efficient. What we mean by numerically efficient is the robust, efficient and robust is that they are not sensitive to small errors in your phi, and that can occur if phi has a high condition number. Anyway, so we have learned what is theoretical least squares problem, the sample least squares problem, and briefly talked about the numerical implementation. When you want to fit a linear model, you do not have to use QR dot solve, you can use the LM. We will come back to that shortly. Any questions on this? All right.